Let's start with the problems. Problems on Newton's laws. Let's. Okay. Suppose you have a box sitting on the floor, such as this. Yeah. So imagine that is sitting on the floor, and let's say the mass of that object is like 2 kilograms. The mass of that is 2 kilograms, and it's sitting on the floor. And if I just momentarily kick that box and give it a velocity of, let's say, 5 meters per second, momentarily, right? I'm kicking it. I'm not applying a force continuously. I'm just kicking it so it moves with the velocity of 5 meters per second. So, in other words, it is beginning to go at 5 meters per second. And you can watch the demo. I'm kicking it 5 meters per second. I don't want to make it topple. So, basically, I'm going to push it to give it 5 meters per second. So, what happened? It slowed down and finally came to stop. How far is that supposed to be? Almost 2 meters. So this box went up to here and stopped. So it went 2 meters forward and stopped. Why did it stop? Now, that's the thought process. You just keep thinking about, why did it stop? I gave it 5 meters per second. Isn't it supposed to keep going? Friction. So friction is involved. What kind of friction is involved? Kinetic friction. Now, I'm asking you to find out the kinetic friction coefficient. See, that is a problem. See how easy it is to bring a problem right in front of you. There it is. The mass of this is 2 kilograms, and I gave you 5 meters per second is the initial push. It went and stopped. Stop means what? Final velocity is? And that's your initial velocity. And I'm saying that it stopped 2 meters away. Question is, yeah, that's a display. So question is, what is the coefficient of kinetic friction? Right? So as I said again, there is no forward force acting on it to keep it going. The only force is the backward force of friction. And this normal reaction is 19.6 and the downward force 19.6, they actually cancel off. That's why this object is not going up or down. Right? The only thing that's happening to it is because I gave 5 meters per second, it is on its way forward, but friction is acting in the backward direction. That is why it slows down to 0. So, given initial velocity, given displacement, and given final velocity, is there a way to find the acceleration? Yes. Go ahead and find it. Find the acceleration. You have initial velocity 5, final velocity 0, displacement 2 meters. Find the acceleration. I can see many of you flipping the pages backward. You should know that those equations by heart.
Sorry, I didn't memorize.
What is the term missing here? Time is missing. Yeah, so we have Vf squared is equal to Vi squared plus 2Ax. You see how the equations of motion are being pulled up again? Depending on the situation, you need to bring them in at the right time. So now we have 0 equals to 5 squared plus 2 times A times 2. So we have 4A is equal to minus 25. Is that right?
Yeah.
So what is A?
6.2.
Minus 6.25 meters per second square. That's in other words, deceleration. Can you see that? So 6.25 meters per second squared is a deceleration. That is why it is slowing down and stopping. So if that is the acceleration acting on this, and you know the only force is this. So that acceleration is caused by what? Or that deceleration is caused by the frictional force. You get it? So what you do is you just take this equation again, and that is what is causing it to be dragged backwards. If this is the deceleration, 6.25 is the deceleration, what is the force? Force is equal to mass times?
Acceleration.
So mass is 2, so 2 times negative 6.25. That's going to be the force creating this deceleration, right? And that is negative 12.5 newtons. So we understand that this frictional force is 12.5 negative. Negative, that's why I'm putting the arrow backwards. You don't have to really take the negative sign when you're just substituting it here, because we know this is negative. So 12.5 is equal to mu k times 19.6. So what is mu k?
Negative points.
No, forget about the negative, because
Yeah.
our arrow backward takes off that negative sign. Yes, Evan? So how much is this? Point? So we found out the coefficient of kinetic friction between that box and the floor. That's one way of finding it out. So you can just create a situation like that and you can evaluate certain things. Yes?
On a question for acceleration, when the acceleration is going down on a vertical question, like an elevator, it's not correlating, just correlating to acceleration.
Okay.
If it hits 9.8, is the object within the elevator pretty much weightless?
Yes.
Okay.
I think we discussed that earlier. Yeah. When the elevator itself is falling at 9.8, everything inside is not supposed to experience normal reaction. The normal reaction tends to be 0. That means everything is pretty much weightless. What is weightlessness? Weightlessness is when there is only one force acting on the object, which is the object's weight. Why am I not experiencing weightlessness right now? Is because I'm acted on by two forces. One is my weight, and the other is the
Normal reaction.
And when that normal reaction is gone, like that is weightlessness. When the marker is in the air, how many forces acting on it?
One.
Only one. That means this marker is experiencing weightlessness. So if you're actually like skiing, suppose you just take off and you're in the air, you're experiencing weightlessness. But again, it is not 100% weightlessness because of the air resistance and other things. Okay? If it is 100% weightlessness, it is just one force. Any questions on this? Right? So this is a variety. You can't say, oh, I can't do this because I've never seen this before. No. There are questions which are absolutely new to you, but then you have to just put your thoughts in. Make a drawing first. You can see what I've done. I made the drawing, put the numbers on the drawing, and then I'm looking at the forces. I drew these forces, and we understood there's a frictional force acting. So I marked the frictional force, put them in terms of an equation, and then we know there is a deceleration taking place. We found the deceleration, which is caused by the frictional force, and so we just get it straight away. No questions? Okay. Now here is a problem. Do you understand the problem by the looks of it? I mean, understand means like not the problem itself, but the situation. What is this?
It's a wall. Ceiling.
Ceiling.
Oh, ceiling.
That's a ceiling.
A wall.
And that's a table sitting here. There's a 10 kilogram block sitting on a frictional surface. It's sitting still. There's a string connected from there. It's not, this time there's no pulley, but it's just knotted here. Another string is connected to the ceiling at that angle. And then you have a bucket of mass, 2 kilograms. You have a bucket of mass, 2 kilograms. Okay? Now, if this is sitting here, this is sitting with the grip. So there's a string trying to pull it forward. But this is still hopefully sitting there. That's because the static frictional force is still building up. And it must be somewhere below the maximum, right? Should be below the maximum. Because this 2 kilogram bucket, I don't know if this 2 kilogram bucket itself is enough to make it slide. That's what I'm saying right now. I'm just expecting that this 2 kilogram bucket is not going to influence this whole thing. Movement, in other words. Now, the question obviously is, how much sand I need to put here in order to get it just started. You get it? So, just started, meaning there's nothing is happening right now. And now there's a 2 kilogram hanging down here. Let's figure out the forces acting on each rope. So first thing is the drawing which is already given to you. Now let's put all the forces down. What forces are acting here? Which is
19.6.
19.6 newtons. Anything acting here? Tension. T1, I'll call it T1. What is acting downward here? T1, downward. On the knot. What else is acting on this knot? Two other tensions. So there is a tension pulling it this way, which is T2. And that T2 is the one which is trying to drag this block forward, T2. And there is another tension here, T3. And T3 is from there also. So actually we have 3 unknowns. And of course there is a frictional force here. Yes. We have a frictional force here.
Can we determine normal reaction?
We can. So we have to put the normal reactions also on it. So first thing is the weight of this, which is 98 newtons. And then the normal reaction is 98 newtons. Some books don't write NR. Some books write FN as a normal force. Some books write different symbols. But you use, doesn't matter. You don't have to worry about which is the right symbol to be used for normal reaction. As long as you understand what is happening. If you write normal NR, everybody knows that it is normal reaction. If someone says FN, it will be a normal force. You get it? Fine. So this is the situation right now. And how do we start working through this is to actually find out this. Now, can you figure out how much is the maximum static friction? What is it? Maximum static friction. Maximum static friction, Fs, is equal to mu s times nr, which is 0.4 times 98, which is 39.2 newtons. So that's a maximum. Now, if my T2 is going to be smaller than this, then it's not going to slide it, right? It's not going to be able to slide it. And when will it slide? When will it actually make it go? When it is equal to this, when it is 39.2, and this tension reaches 39.2, and from then on, it will slide. You get it? Now, once it starts sliding, no one can stop it because it changes to kinetic friction, which is actually smaller than this, and therefore it will keep sliding. Once it begins to slide, it's going to slide on. So, if I take this as 2 kilogram only without anything in it, probably the tension T2 is not enough to pull it out, right? So now what we're going to do is, instead of taking it as 2 kilograms, we are going to take what is the whole thing. Let me call it M. So in that case, this 19.6 is going to be removed and marked as
MG.
mg or 9.8 m. Isn't it right? 9.8 m, which is mg. If someone is not clear with this, tell me. The weight is m, capital M, times g. G is 9.8. I'm already using it there. So I don't want to keep g along with me. Now come back here. We're looking for the moment it slips. So what is T2?
39.
So that is 39.2, which means this is 39.2. So our T2 is already known that we need the max, so 39.2. So I'm not going to solve for T2 anymore. I don't want to. What are we trying to solve for? We're trying to solve for mass. Here, acceleration is not our concern. Acceleration is not a concern. So if this is 9.8 m, T1 is what? Since it is at rest. 9.8 m. So T1 is also 9. So instead of writing T1, I'm going to write it as 9.8 m. That's what is going downward. That leaves us with only one unknown tension, T3. So how do you do it from here on? We're going to consider this knot to be at rest and in equilibrium. What do you mean by equilibrium?
All forces completely cancel.
All forces in the x direction must be equal to 0. All forces in the y direction must also be equal to 0. So that's what we're going to do now. So net force in the x direction must equal to 0. Net force in all the y directions must be equal to 0. This is because you know this knot is not moving and is in static equilibrium. What is the difference between static equilibrium and kinetic equilibrium?
Things can move with various kinetic equilibrium.
What kind of movement?
Constant.
Constant velocity. So if something is at rest, like this, if this thing is at rest now, in my hands, there are two forces acting. There are two forces acting on it, and it is at rest. It's a static equilibrium. Now it's moving at a constant velocity. That is kinetic equilibrium. Get it? Alright, so since we know that it's an equilibrium, we need to take all this and equate it to 0. So make your table x and y. We'll figure out each one at this knot. What is the x component of this force here?
39. Negative.
Negative 39 point. So negative 39.2. And what's the y component of that? 0. Now let's look at this one. What is the x component of this?
0.
0. And y component?
Negative 9.
Negative 9.8 m. And that one. Now we need to split it. That's why I give you the angle. So 50 degrees. So what component of T3 is acting this way? T3 cosine 50. What is the component upward?
T3.
T3 sine 50. And then put it down. So this one is positive. So it's a positive T3 cosine 50. And this one is also positive T3 sine 50. Those are the forces acting on this knot. And it is keeping it in static equilibrium, which means the net force must be 0. So what you have to do is now equate these. Equate those. So if I add this up and equate it to 0, you get T3 cosine 50 is equal to 39.2. Is that right? If I add this and equate it to 0, I can shuffle it up and make it that way. Over here, the equation on this side, let me pull this back. T3 cosine 50 is equal to 39.2. I'm going to write this one above this. What do you write here? T3 sine 50 is equal to 9.8 m. Is that okay so far? Now see what I'm going to do to solve, because I'm not concerned about T3. I'm just going to divide this expression by that. Just divide equation 1 with equation 2. What happens to T3? Out. What is sine 50 over cosine 50? Tangent 50 is equal to 9.8 m over 39.2. Can you figure out m from there? Do it. Figure out m. So tan 50.
Negative 1.09.
Negative. Oh, make it radian degree. Tan 50 is always going to be more than 1. Because tan 45 is 1.
4.77?
This one? Tan 50?
No, just the overall.
Oh, the answer?
4.77 overall.
So 4.77 kilograms. That's what you end up getting for mass. Mass what? Mass of the whole thing. So how much sand has to go in?
2.77.
That's it. So the answer is, if you put 2.77 kilograms, if you keep adding sand into it, as soon as you reach 2.77 kilograms of sand, it's going to slip. Yeah.
So can you go over the steps again from how you got from 1050 equals 9.8?
Oh, here? Just cross multiply it. Just cross multiply those two. So 9.8 m is equals to 39.2 tan 50. Therefore, m is equal to 39.2 tan 50 over 9.8. You'll get that. So 4.77, you've done the calculations right. Is it right?
Yeah.
So 4.77 is the total mass hanging here. So since the bucket is already 2 kilograms, all you need inside is the 2.77 kilograms of sand. As soon as you put 2.77 kilograms, immediately this will start sliding because it will reach 39.2. As soon as this reaches 39.2, that's when the friction just comes out. Okay. Now see this variety. This is not Newton's second law. It's first law. You're using the first law. And see, when you look at the situation, you'll find out if it is moving or not moving. And then is it moving at a constant velocity, or and then you can figure out which law to put in and how to proceed. Yeah.
Would we be told in the problem that the knot was at equilibrium?
Yeah, you'll be told. Or even if you're not told, if you're asked how much sand is required to make it just slide. So what is happening before that is not sliding. And if it is not sliding, the knot is in equilibrium. Clear? We did a problem with the boy is hanging on the knot, right? It's a kind of similar thing, but you're using different tensions here. Now in this case, the tensions, like we got rid of the T2 and we got rid of T1 because it's not moving yet. And the only thing was T3, which was not known to us, but we didn't want to know it. We just cancelled it out. If you really want to know it, you can just use it from here. See? T3 cosine 50 is 39.2. You can figure out the tension from there straight away. T3 will be 39.2 divided by cosine 50. And that will give you something around 80s, 90s. The tension here will be around 80s or 90s. Yeah.
I took the new mass of the bucket with the sand, which is 4.77, multiplied it by 9.8, and
Okay.
got me 46.75 newtons. That's more than the static friction.
No. Once again. Oh, yeah. You don't have to worry about the numbers. This weight here is entirely independent of that one. The tension. What's the tension here? Can you do that calculation? Use this equation. T3 cosine 50 is 39.2. Therefore, T3 will be 39.2 divided by cosine 50. Do it. Huh?
61.
61? So this tension is 61. And this tension is 46 something, right?
so
Yeah, so this 46 something, that's 61, and this entire this 39.2. They're all different. Why they are different? Because they are all different strings. It's not one string. So you cannot compare with that. So just because this 46 something, you can't say, oh, isn't 46 point something greater than 39.2? You know, but this is in some other direction. That's why we are resolving the forces in the x and y directions and all that. Okay. All right. So we have two inclined planes now, and a pulley right there. Now we have two objects, 10 kilograms, 10 kilograms, and the coefficient of kinetic friction is 0.05. You know what I'm going to ask. What's the question? Which way is it going to move? What's the acceleration? Which way do you think it's going to move? Possibly this way. Because sitting on a greater slope, that is sitting on a slight, less steep slope. And therefore, this will have more mg sine theta pulling it down compared to that. And that's why you can expect it to accelerate. But before you do that, mark all the forces. That's the next thing to do. So the problem is already on the board, and the coefficient of kinetic friction is the same for both surfaces. So mark all the forces. Instead of marking all the forces, instead of drawing the weight itself, you don't have to draw the weight. What are the two things that you need to draw? Mg sine theta. Can you tell me how much it is? What is mg sine theta here? It is 10 times 9.8 times sine 30, which is that's 49 newtons. Now, what is the normal reaction here? Normal reaction is going to be mg cosine theta, which is how much? 84.9. And then this one's mg sine theta is what? Mg sine theta equal to 98 sine 50. 75.1. And the normal reaction here is mg cosine 50. Huh? 63.6? 0. 63.0 newtons. And now you know what to do. We are expecting it to go this way. And therefore this is expected to go this way. So which way will you mark your friction on? The opposite direction. Since it's going this way, you mark the friction here. And how much is the kinetic friction? It is 0.05 times normal reaction. That's a normal reaction. So what is 0.05 times 63? Yeah.
How did you get 49 newtons for the
mg sine theta. 10 times 9.8 times sine 30.
Why would you sign for that?
That's the downward component.